All right, last example. It's going to have to do with water going into a conical container. Okay. You may have seen in different places, sometimes when there's a water dispenser, the cups are in the shape of a cone rather than, a usual cup shape. So imagining water pouring into a conical container you're kind of seeing that more and more nowadays, actually. All right, so what does it say? The water is poured into a conical container, vertex down. So that's what this picture is reflecting. At the rate, rate. I have to pay attention to the word rate. Rate of 2 cubic feet per minute. All right, 2 cubic feet per minute makes me think of volume. Let's keep reading. The container is 6 feet deep. Okay, 6 feet deep, that makes me think of like the height of the container. So maybe I'll label that. So the height is 6 feet. And the open end is 8 feet across. The open end is 8 feet across. Okay, so let's see. 8 feet across looks like they're talking about this length. All right. Question is, I see a question word in the next sentence. So this is where I'm going to see the thing that is what I am being asked to find. How fast is the level of the water rising when the water is 3 feet deep? All right, let's label this water. So the water, when it's at the height of 3 feet, we're being asked how fast is the level of the water rising. So level of the water is the height, the change in the height. Okay, so we're thinking of this change. The water's rising. Okay. As you might have noticed, there's this equation over here on the right. This is one of those geometry formulas you just have to remind yourself about. This is the formula for the volume of a cone. You'll see V, which is volume, R, which is radius. Those are two familiar letters. And then there's this other one, which is H, which stands for height. Okay. So instead of labeling this with 3 feet, I want to have as general a setup as possible. So this height of the water, the level of the water, is H. The change in that level is dH dt. Okay. So we have an equation. We're going to use that. V equals 1/3 pi r squared h. And this is another one of those that when you get to Calc 3, you'll learn how to derive this equation. We take the derivative of both sides of this equation, just as we've been doing in all of our other examples. Now here's the thing. We have we have 3 quantities that are varying with respect to time. We have the volume, V, is varying with respect to time. We have radius, which is R. The R I've just mentioned is the radius of this conical part. And that radius is changing. If you imagine a higher and higher level of water, you're going to have that radius change. We also have, let's see, we have volume, we have radius, and we have height. I think I got my color codes wrong. height I called h, and volume I think we called it v, and we made it in green. Okay. Anyway, those are the three quantities that are changing. All of these are functions of t, which means when we do derivatives with them, we have to keep that in mind. That's one of the things that's going to make this example different. All right. Back to taking the derivative of both sides. We have now dv dt on the left-hand side. We have 1/3 pi on the right-hand side. I'm going to just leave that alone, and because those are constants, and then I will write d dt of r squared h. All right. Ask yourself for a quick moment, what's about to happen here? Which derivative rule am I going to have to use, given the fact that r and h are both functions of t? Okay, hopefully you said product rule. So using the product rule on the right-hand side and copying everything else that I haven't dealt with yet, I'm now going to have derivative of r squared, which would be 2r dr dt times h unchanged, plus r squared times the derivative of h with respect to t. So I did the version of the product rule where you do derivative of the first times the second plus derivative of the second times the first. I hope that wasn't confusing. Let's multiply things out and see what we get, but I need a little bit more room. So I'm going to give myself room. Whoops. Okay. All right, so dv dt equals, let's see, 2/3 pi r h dr dt plus 1/3 pi r squared dh dt. Looks complicated, but we have a lot of what we need. We just have to plug it in. Okay. All right, so let's figure out what we know and what needs to go where. Going back to the problem, we have, let's see. Okay, so it's asking how fast is the level of the water rising when the water is 3 feet deep. The depth or the height of the water is h. So we know that h is going to be 3 when we plug it in. Earlier in the problem, we have that the volume is increasing at a rate of 2 cubic feet per minute. How do I know it's increasing? How do I know it's positive? It's saying water is being poured into the container, not being drained out of it. Okay, so dv dt is 2. I'll plug that in there. So we know h, we know dv dt, and the rest we don't know. But we know we're trying to solve for how fast is the water level rising. Maybe it would help if I wrote that over here. We want dh dt. Okay, we have dv dt is 2. We have h at the moment we care about is 3. And we have nothing else because we can't use this 8 feet right now. This is not helping us at the moment. We can think of ways to find this radius, and I'll go through that right now. Okay, so if It's 8 feet across. That means this little portion here is 4 feet. Okay. Let's make a triangle out of this situation. If I make a triangle out of this, notice I have this R, that's a mystery. I have a 4 up here. Let me draw that. Write that 4 better. 4. The height of the whole thing is 6 feet, which means this length here will be 6. And what I want to know is this little piece here. And I want to know this radius r. Oh, but wait, I have this quantity here. This is h, and it's saying at the moment when h is 3. So actually, I do know that. That is 3. All right. We're going to use one more thing from geometry right now, which is the idea of similar triangles. I have 2 similar triangles here, the big one and this smaller one. Notice that this corresponding piece is half as much as this corresponding piece, and that tells us that this top piece, the 4-foot side, is double this r here. Okay, what that tells us then is when h is 3, r is 2. Okay, great. So we have h is 3, r is 2, dv dt is 2. We have r, which again is 2. And we want dh dt. Great. That means we can plug in everything we know and finish the problem. Let's do that. dv dt is 2. And then that equals 2/3 pi times r, which is 2, times h, which is 3, times dr dt. Oh, wait a minute. We didn't think about that. What's dr dt? I'm going to use the fact that we have this similar triangle situation to help me answer that. Okay, let's think about it. We know that the relationship between r and h is like a 3-to-2 kind of relationship. More precisely, r is equal to 3/2. Oh, sorry, not 3/2. That's backwards. R is smaller than h in this situation. So r is actually 2/3 of h. And the reason this makes sense is when h is 3, r is 2. So if I take 3 and multiply it by 2/3, I get 2. And this happens throughout the whole triangle here. When h is 6, if I take 6 and multiply it by 2/3, I'm going to get 4, which is r. Why does this help us? Well, if I take the derivative of both sides of this little equation I have off to the side, I have that dr dt is actually equal to 2/3 times dh dt. Okay, so I can substitute that in right here. 2/3 dh dt. Again, we still don't know what dh dt is. It's what we're trying to solve for, but that's okay. We are getting closer. All right, the next term in this equation that we've been working with, so we're back to this equation and plugging in what we know, is we have 1/3 pi r squared, remember r is 2, times dh dt. And why don't I make it in purple, since that's what we want to find. I'm going to simplify what we have. We have 2 equals 2 times 2 times 2 8/3 pi dH dt plus, let's see, 4/3 pi dH dt. Oh, that's pretty nice. We get 2 is equal to 12/3 pi dH dt. And 12/3 is just 4, so I have 2 equals 4 pi dH dt. I'm going to divide by 4 pi on both sides. I'm going to get dH dt is 1/2 pi. Our final answer, we want to write it as a complete sentence. So the final answer would be the height or level of the water is increasing at a rate of 1/2 pi. What were our units again? Feet per second, I believe. Feet per second. Let's double check those units. Oh, per minute. Sorry. Let me fix that. Per feet per minute. And there you have it.